Dear students, in the last class I have explained the refraction through a curved surface, and the relation related to the refraction through a curved surface is minus n1 by u plus n2 by v is equal to n2 minus n1 by r, where n1 is the refractive index of the object space, u is the object distance, n2 is the refractive index of image space, v is the image distance, and r is the radius of curvature. So, what is the object space? Space containing the incident ray is called as object space. What is image space? Space containing the refracted ray is called as the image space. Based on this topic, so we have a numerical. So, let us try this numerical right now. So, the question is this: a mark placed on the surface of a sphere. So, let us take this is the sphere, and there is a mark. Let us consider here there is a mark. So, this is that mark. Sphere is viewed through a glass. So, this is a glass sphere, glass from a position directly opposite. It is viewed from here. So, this is the eye of the observer from a position directly opposite. If the diameter of the sphere is 10 centimeter. So, diameter is a 10 centimeter. So, radius is 5 centimeter. So, later we will apply the sign convention, and refractive index of the glass here, the refractive index of the glass is 1.4. Find the position of the image. So, we have to find basically the image distance, which is a v. So, this is what the question. Now, when the object is here and when the observer is observing that object from here, so this is the reference point, which is the pole, because all the distances are measured from the pole. So, what is that equation? Equation is minus n1 by u plus n2 by v is equal to n2 minus n1 by r. So, we need to find n1, n2, u, v and r with the proper sign convention. So, object is here. So, this is the incident ray. The incident ray will be something like this. So, incident ray will be inside the glass. So, therefore, that acts as object space, whose refractive index is given 1.4. The refracted ray will be here outside the glass, which is in air. So, refractive index of the image space is 1, because how do you define image space? Space containing the refracted ray. The refracted ray is here. Object distance. So, object is this. This is the object now. So, it is at what distance from the pole? It is at the distance of 10 centimeter. So, use the sign convention. What is the sign convention? The sign convention is, if this is the incident ray, the distance is measured in a direction opposite. So, that is what is minus sign. So, we have to find the image distance, because the image distance is not given. So, what is the radius of curvature? The radius of curvature is 5 centimeter. What is the sign for it? See, this is the center of curvature. The radius of curvature is measured from a pole like this toward the center, which is in a direction opposite to the incident ray. So, again the sign is minus. So, it is a direct substitution problem now once we write all the data. That is minus n1 is 1.4 by u, which is minus 10, plus n2 is 1 by v, which we have to find, is equal to n2 minus n1, 1 minus 1.4, which is minus 0.4, by radius of curvature, which is minus 5. See, I am substituting here everything in centimeter only, so that even the final answer what we get is also will be in centimeter. This minus of minus here becomes plus. 1.4 by 10 is a 0.14 plus 1 by v. This is also positive, negative divided by negative. 0.4, so that will be 0.08, 4 by 5 0.08. So therefore it is 1 by V. So 1 by V is 0.08 minus 0.14. So the difference is negative 0.06. But that is 1 by V. We want to find the value of V. So V is equal to minus 1 by 0.06, which is same as minus 1 by 6 into 10 to the power minus 2, correct? And when you take that 100 to the numerator, it becomes a minus 100 by 6, which is 50 minus 50 by 3, correct? Minus 50 by 3. So 50 minus 15 by 3 is minus 16.67 centimeter. So here it's so 3 ones are 3, correct? Yeah. So 16 threes are not 16. It's a 6 point, correct? No. Let me divide this. So 3 ones are 3. Yes, so 16.67, correct. So that's what you get. So much centimeter. So negative sign indicates that the final image formed is a virtual image. Okay. Virtual image will be formed at a distance of 16.67 centimeter. We don't write minus sign now. From P, from pole. Okay. So that's how we get the image. Fine. So this is the application of that derivation, which I have derived here in the last class. So hope all have understood. And let's see more about this particular chapter. We are going to learn about a device, and the device is called lens. What is a lens? Lens is an optical medium which is bounded by two surfaces, out of which at least one is spherical. Lens is an optical medium bounded by two surfaces, out of which at least one is spherical. So one such lens is this, where there are, you can see both the surfaces are spherical. And if I cut this, I'll get this shape of the lens. So we have another lens, and again if it is cut, we get this type of the lens. So these are the different shapes of the lens. The lens which is thicker at the center and thinner at the edge. So this is called biconvex lens. A lens whose one of the surfaces is plane and the rest is convex. It's called plano-convex lens. Lens which is thinner at the center and thicker at the edge is called biconcave lens. And if one of the surfaces is plane, it's called plano-concave lens. Then we have two lenses which is a combination of convex as well as concave. This is called convexo-concave lens, and this is called concavo-convex lens. So these kind of lenses are highly used in the spectacles, okay, so to correct our vision. So these are the type of lenses which are used, okay. So let's see more about the term, the lens, and what are the new terminology associated with this lens. So I'm going to consider a convex lens, and this is the principal axis. When we take an incident ray on one of the face, after the refraction through the lens, it emerges parallel to the incident ray. Then the ray which cuts the principal axis inside the lens, now this is called the optic center of the lens. So optic center of the lens is a point inside the lens where the refracted ray cut the principal axis. But if the lens is a very thin lens, where thickness is negligible, then any ray passing through the optic center, this is the optic center, okay, any ray passing through the optic center passes undeviated, passes straight without any deviation. Only in thick lenses, the incident ray and emergent ray are parallel. We'll get some gap between the two. That's only in the case of thick lenses. But the kind of the lenses which we are learning, which we are studying, or which is part of our syllabus, is the thin lens. So therefore, if at all any ray passes through the optic center, it has to pass straight without any deviation. So that's the point which you have to remember. If I consider a parallel beam which is allowed to fall on a convex lens, so this is the convex lens, this is the principal axis, and if a parallel beam is allowed to fall on a convex lens, after the refraction, they all converges to a particular point, and this particular point is called as principal focus. In the case of concave lens, if a parallel beam is incident, after the refraction, the rays appear to diverge from a point which is behind the lens. That point is also called as principal focus. So what is the principal focus? When a parallel beam is incident, paraxial rays are incident on a convex lens. After refraction, they converges to a point, whereas in the case of convex lens, the rays appear to diverge from a point, and that point is called as the principal focus. So we have an optic center here for both the lenses, and the distance from the optic center to the principal focus is called as the focal length of the lens. Distance between the optic center and the principal focus is called as the focal length of the lens. And according to the sign convention, here the principal focus is in the direction of the incident ray. Here the principal focus is opposite to the direction of the incident ray. So here the focal length of a convex lens is always taken as positive, whereas the focal length of a concave lens is taken as negative. Reciprocal of the focal length is called as the power of the lens, optical power. This power is measured in terms of a unit called diopter. Capital D is the symbol used for that. So power is in diopter only when the focal length is in meter. Power is in diopter only when the focal length is in meter. If the focal length is in centimeter, do the conversion, and then you can write the power in terms of the diopter. Diopter is the special unit for optical power. So for other power, like we have mechanical power or electric power, the unit is watt. So this is the optical power. So now again, according to the sign convention, power is positive for a convex lens, power and focal length, whereas power is a negative and the focal length is negative for a concave lens. So whenever we use specs for our correction, correction of the vision, so there will be some power for both the specs, correct? So positive or negative. So and you should know it. So they will come to know what kind of lenses are using it. So the power of the lens which I am using is about plus 2.25 plus indicates that. So this lens which I am using, it acts like a converging lens, this acts like a converging lens, which is convex lens. If your power is negative, then uh, the lens which you are using, it acts like a diverging lens or a concave lens. It acts like a concave lens. Okay. So these terms are important, the focal length and the power. Now, so related to the mirror, so we have a formula which is 1 by u plus 1 by v is equal to 1 by f. This is called mirror formula. Now this is not part of the syllabus because that's deleted, mirrors are deleted. Then what is this formula? This is called mirror formula, where u is the object distance, v is the image distance and f is the focal length. So we have a similar formula called lens formula, which is minus 1 by u plus 1 by v is equal to 1 by f. The sign that we need to change here is for the object. So here it's a plus, here it is a minus. Minus 1 by u plus 1 by v is equal to 1 by f. Object distance, image distance and focal length. So this is called mirror formula, this is called the lens formula. Now here, when the object distance is increased, this one, image distance here, when this is increased, correct, when u is increased, this value of v also increases, understood, so that this f remains constant. Okay, not increase, when u is increased, v decreases so that f remains constant. So there is no change in the value of f. F is a constant, so f is independent of the object distance and image distance. If this is increased, the other value, imagine if this is increased twice, then this decreases twice, correct, so that the value of f remains the same, no change in the value of the focal length. Then the question comes, what are the factors on which the focal length of a lens depends? So for which we have a formula that gives you an idea regarding the factors deciding the focal length of a lens. So this is an important derivation, and this is called the lens maker's formula. It's called lens maker's formula. So to derive this, I'm going to consider a thin lens. Even though it looks thick here, it's a thin lens. This is the principal axis, and ABC is one of the curved surface and ADC is the other curved surface. N1 is the refractive index of the surrounding medium and N2 is that of the material of the lens. Now here we are going to use this particular formula, which is refraction through a curved surface. That's minus refractive index of object distance, I'll write OD, object distance, divided by the object distance plus refractive index, sorry, not object distance, object space, okay, object space, divided by object distance plus refractive index of image space by image distance, that's equal to refractive index of image space minus refractive index of object space divided by the radius of curvature. So this is the formula which is used. Now whenever refraction takes place through the lens, there are two curved surfaces are there, one ABC, other is ADC. And this formula is applicable, only for single spherical surface. We can't use this formula straight away for both the surfaces. So I have to use this formula once for the surface ABC and again use the same formula for the surface ADC. So then relate all the equation, because this is the expression used to find the refraction through single surface, one surface. But in a lens we have two surfaces. So what I'm going to do is, so when refraction takes place through the first surface, I will assume the absence of the second surface. So just assume that there is no second surface. So that now the refraction takes place from n1 to n2, and let's assume that this is continuously, this is continuous, this is n2 only. Imagine single surface and this is single medium. So n1 to n2, now refraction is from n1 to n2. So for which you consider an object O at a distance u, and now the distance are measured from the optic center, and this is one of the incident ray which passes straight without any deviation because it passes through the optic center. You take another ray very close to it, okay, at a point, let's consider something like M, and now the refraction takes place at that particular point. So the ray undergoes refraction, and then these two rays meet at a particular point called I dash, which is at a distance V dash, not V dash. So now see, whenever the refraction takes place, through the first surface, through ABC, which is the object space. Object space is the space containing the incident ray, which is N1. Image space, space containing the refracted ray, which is here, which is N2. So N1 is the object space, this is the image space, and N1 is the refractive index of object space, U is the object distance, N2 is the refractive index of image space, and V dash is the image distance. And since the refraction is through the first surface, R1 is the radius of curvature. So I can use this particular formula. So minus refractive index of object space. Object space is the space containing the incident ray, which is here. So it is N1 by U, which is object distance, plus refractive index of image space. It has to be the second one, other N2. And remember, I am assuming that this is a continuous surface, N2, because we have already assumed that there is no second surface. Okay, it's a single surface. So I am using this particular formula, N2 by. Now image distance is this V dash. So what kind of image do we get here? This is a real object because the rays really diverge from a point, real object. This is a real image. Why it is a real image? Because the rays after the refraction really converge to point I dash. So real object distance, this is real image distance. That's equal to refractive index of image space is N2 minus N1 by R1. So this is one of the equation. So now most important, the refraction through the second surface. So now let us assume that, we don't have to assume as such, we know that there exists a surface actually, it's a real surface, right? So now how the refraction takes place through ADC, Now this is important. See, once the refraction takes place through the first surface, we get a real image at I dash because we have assumed the absence of the second surface. But since there exists a second surface, when the ray falls here, this will not go, like this continuously. That ray will not go continuously like this. Why? Because there exists a surface, there is a real surface. So that means that whatever the ray that we have drawn here has to be imaginary. So therefore, you have to draw dotted line. Initially I had drawn continuous line because in the absence of the second surface, the ray will pass straight without any deviation, correct? So that's why I have drawn continuous. But now, whenever the refraction takes place at the second surface, the ray falls on the second surface and it undergoes refraction now further. And it forms a final real image at I. So this is the final image. Actual image what we get is this. This is a temporary image formed during the refraction through the first surface. Now this is the incident ray. For the second surface, this is the incident ray. And where that incident ray is? The incident ray is in a medium N2. So therefore now this N2 acts as object space. This is the image space. Okay. Earlier the refraction was from n1 to n2, right? It was from n1 to n2, where n1 acts as object space, n2 is the image space. Now the refraction is from n2 to n1, so that means the n2 acts as object space and n1 is the image space. And final image, let us take at a distance of v. So since this is the incident ray, for this incident ray, this I dash, now it acts as an object. What kind of object? Virtual object. For refraction through the second surface, I dash acts as object. What kind of object? Virtual object. And for that virtual object, we get final image, which is I, that's a real image. Therefore, that I dash is a common for both first as well as second surface. That I dash acts as a virtual object for second surface only, but for the first surface, it's a real image. I've already told you. I dash acts as a real image for refraction through the first surface, or for second surface, it acts as the virtual object. So therefore now, refraction through the second surface minus refractive index of object space. Object space is this, because here there is an incident. So since this is the object space, N2 is the refractive index, divide by, which is the object now? Object is I dash. What kind of object? Virtual object. So what is this distance? V dash. So minus N2 by V dash plus refractive index of image space. Image is formed here at I, at a distance V, and this image I is formed here in a medium of refractive index N1, because that's the surrounding medium. So therefore it's N1 by V. So that's equal to refractive index of image space, which is N1 minus N2 by R2. So this is the next equation. So I will just rewrite this equation again, minus N2 by V dash plus N1 by V, and now take minus sign outside and then you write it as N2 minus N1 by R2. This is the third equation. Clear? Just because when we add, so this should be common right here. N2 minus N1 is there. So here we have N1 minus N2. So that's why to write in that same format, I took minus sign outside. Now you add equation 1 and equation 3, this and this. So when you add this and this, you can see here, we have N2 by V dash plus N2 by V dash minus N2 by V dash. That will get cancelled. What remains is only this, minus N1 by U plus N1 by V is equal to, for this, N2 minus N1 is common. And what we get is 1 by R1, 1 by R1 minus 1 by R2. Correct? So next, N1 is common, so we get minus 1 by U plus 1 by V is equal to N2 minus N1 into 1 by R1 minus 1 by R2. Now if you look at this particular term, minus 1 by U plus 1 by V, that is nothing but 1 by F, which is from the length formula. So this is 1 by F is equal to, bring this N1 to the right, so you'll get N2 minus N1 by N1 into 1 by R1 minus 1 by R2. So therefore the final expression, which I'll write here, is 1 by F is equal to, you can divide both the terms by N1, so that you will get 1 by F is equal to N2 by N1 minus 1 into 1 by R1 minus 1 by R2. So that is the formula called as lens maker's formula. Why it's called lens maker's formula? Because in designing the specs with the power, so this formula is of great use. So by changing, so just look at the equation. What are the factors on which the focal length or the power depends? Okay, I will write that formula here. One by F is equal to N2 by N1 minus 1 into 1 by R1 minus 1 by R2. So what are the factors? And 1 by F is nothing but power, correct? 1 by F is nothing but power. So power or focal length depends on the radius of curvature of the two surfaces, where R1 is the radius of curvature of the first surface, R2 is the radius of curvature of the second surface. Not only that, it depends on N1 and N2. N1 is the material of the lens, correct? N1 is surrounding medium, N2 is that of the material of the lens. So it depends on what kind of material this lens is made up of, okay? That is N2, refractive index. So that changes the focal length and depends on the surrounding medium. Whenever we wear it, the surrounding medium is air, but if we dip our face, inside water, then water acts as the surrounding medium, correct? Then the power and the focal length changes. So that's why we are unable to see if we immerse our head inside water, okay? So what are the factors that decide the power and the focal length? Refractive index of the surrounding medium, refractive index of the material of the lens, and the radius of curvature of the two surfaces. Suppose if the surrounding medium is air, if the surrounding medium is air, then we write the formula like this: P is equal to 1 by F into 1 by F is equal to, this N1 becomes 1. So instead of writing N2 minus 1, we write N minus 1 into 1 by R1 minus 1 by R2. So this is the formula when it is surrounded by a medium, and this is the formula when surrounded by lens is surrounded by air, okay? So important derivation of this particular chapter. So one of the derivation is refraction through prism, then refraction through a single curved surface, and this is the other important derivation, which is refraction through a convex lens, or it's also called lens maker's formula. And in the examination, you have to even take care to see that these lines which are drawn are dotted lines, okay, not because they are imaginary, they are not the real lines. The real refraction is like this, from O to M, correct, and then M to another point here, and then back to I. So that's the real refraction, and this is imaginary, temporarily, in the absence of the second surface, how the refraction takes place. To understand that, we have drawn that particular point. And for refraction through the first surface, O is the object, real object, and I dash is the real image. That is for refraction through first surface. For refraction through second surface, I dash is the virtual object and I is the final real image. Even the variable also you need to consider properly. U, V dash, and then V. This is how you have to consider the variable. So hope you have understood the derivation. So more about this refraction, there are some more numericals are remaining, so that I am going to explain in the next session. So again, a reminder to all of you, so don't waste your time much. So revise any subject, not only physics, but all the subjects. So there will be examination, so we are not sure about the date, but once everything get settled, so that